Well, question 1 here asks us to use Maple and evaluate the possible limit, and to verify our results graphically, numerically, and algebraically. And so we're going to be finding the limit using these 3 methods: graphically, numerically, and algebraically. And so when we get started, you can say that this is our Lab 2 sample. And you know what? I do have some sample problems I can do that are going to make this easier so I don't have to make up sample problems. You grab those real quick. Actually, I think it's these same ones that are here. Yes, it is. All right, so for the first one, instead of doing this problem, I'm doing the same limit as x approaches 1, but my function is going to be slightly different. My function is going to be this x minus 1 over x squared minus 1. So that will be the difference in our function. So for my number 1, my f of x will be x minus 1 over x squared minus 1. And I'll zoom in a little bit here. And reminder that our goal is to evaluate the limit graphically, numerically, and algebraically. So we'll do graphically first. And graphically, we just want to plot, right? So we just need to write our plot. We can plot our f of x without really giving it much details. But we can write discont equals show removable, because that's going to show us if we have any removable discontinuities. And we can see here that, hey, we do have a removable discontinuity, specifically at 1. And what we're trying to do is find the limit, right? We're trying to evaluate the limit here, which is essentially what is the y value when x is 1. And so here, it's a little hard to guess it. So what I'm going to do is get a little closer to the x value. So I'm going to say x equals 0 to 2, right? I'm picking numbers slightly below 1 and slightly above 1 so that I can see what's going on at 1. And now with this picture, I can see a little more clearly that, hey, as x approaches 1, my limit seems to be about half. So I could say the limit as x approaches 1 for f of x is about half, right? Because this looks like when we're at 1, we're about at 0.5 or half with the y value. Anybody have any questions for this for this graphical approach? Awesome. Moving to the numerical approach. So the numerical approach is essentially us plugging in values close to this 1 value and seeing if they confirm this thing that we just found. And so we can make a table in Maple, so that way we can just put all our values in a row. And the way we make a table is by going to Insert and then Table. So for everyone, just go to Insert and Table. That's how we can make a table. You're going to want to have 2 rows and 7 columns. So 2 rows and 7 columns. Once we do this, we get this table right here. Reminder, the way I did this is I went to Insert, then Table. I made a table with 2 rows and 7 columns. And so I'm going to name my rows x and my, I'm going to name one row x and my other row f of x. And then my columns are just going to be the values that I'm plugging in here. So let's say, so some numbers close to 1 would be things like 0.9, 0.99, and 0.999. And then now from above, it would be 1.001, 1.01, and 1.1. And so these are just some values that are close to 1. Of course, we could have picked something slightly different. But these are just the general values that we tend to use when working on limits. So these work. And now if I want to plug these in, I can do f of 0.9 like this, and it gives me my value here, my f of 0.99 here, my f of 0.999 here, etc. So I'm just plugging the values into all of them. And if you're wondering why this has 2 rows on it, it's just because it doesn't fit on 1 row. So if I was to zoom out, everything will look fine. It's just a long number, and so when I zoom in, it puts it in 2 rows. So don't worry about the fact that it overflows into the 2nd row. The thing that we want to know is, as we get closer to the center here, as we come to the center from both sides, what number are we approaching from both sides? And this here confirms that, the limit as x approaches 1 for f of x is 1 over 2. So any questions are on our numerical approach?
I missed the table. How this table can be in this?
Yeah, so we want to go to insert and then table.
Oh, I see. Thank you.
We pick 2 rows and 7 columns. You can of course pick, I think we need 2 rows. I don't think we need more. But you can pick the number of columns that works depending on how many numbers you want to put from the left and from the right. I say 7 columns because then we can do 3 from the left and 3 from the right.
I see. Thank you.
Yeah. Any more questions before we move on from the numerical approach? All right. And so our remaining approach here is the algebraic. I don't even know if it's spelled. Oh, there's an E in it. All right. So yeah, algebraically. I don't know if that's spelled right, but I'm gonna assume it is. For the algebraically, we're actually just using the command that Maple has built for limits. So in other words, when you use the limit command in Maple, Maple does any canceling, simplifying, all that good stuff, and then plugs in the number for you. So what we want to do is use the limit command to solve this problem. And to do that, we just want to write limit, and then the equation we want to solve the limit for. So in this case, it's our f of x, and then the limit value. So in this case, it's x equals 1. And so we see that we get our response of 1 over 2, which is what we expect since we have received 1 over 2 for our limits prior. So this is all we need to do for our algebraic approach. I'm going to note here, I'm going to put a note here, some notes. Just because in some future problems, it may be helpful to say, hey, what is the limit from the left and what is the limit from the right? And you can also do that with Maple, using the same exact command, but then just adding a comma here and then writing either left or right. And so this would give us our left-hand limit or our right-hand limit. If you want to see what it looks like symbolically, you can put the capital L and it will show it to you symbolically. So just to make sure that it's looking good. But yes, left limits and right-hand limits you can find using by adding a comma then left and right. This finds a 2-sided limit. So if you don't put any comma direction, it finds you the 2-sided limit. And one other note in the sum notes section here. There's another way of doing limits using these helper functions, I guess you would call them, here on the left. You can click on this thing that says lim x approaches a for f and fill it out. So in this case, I want my limit as x approaches 1. I can technically put the function here, like the entire function here. So let's say my function was x squared minus 1 over x minus. Is that what it was? No, it was the other way around. Yeah, so you could technically plug it in just like that, and it'll do it for you. You could also plug in lim as x approaches 1 of just f of x. If you have f of x defined, then it, of course, does the same thing. So just some notes on how we can find the limit, getting the same answer. This right here is already sufficient. But in case you don't like using the limit command, maybe you forgot like what the word is in the future, you just know that, hey, I can come here on the left and click on this limit, and it does the same exact thing. Any questions here on our algebraic approach? All right, we're gonna move into number 2 then. Number 2 is very similar to the first problem in lab 1, where it asks us to find discontinuities, if any. For each discontinuity, indicate whether it's removable or non-removable. And then lastly, using Maple, we're going to verify results graphically. This is the part that's extra. It says, then confirm your results algebraically by evaluating the appropriate limit. So essentially, part A and B, essentially the same. Part C, kind of the same, because we do still want to graph it, but we get this extra little ask of use the limit command to solve any of those discontinuities to confirm that they're what we said we are. And so we're gonna tackle this first one here. I have the sample problem somewhere down here. We have f of x is x squared plus 2x. All right, so then this is our sample problem. And we want to go ahead and find the discontinuities, if any, for the following function. So first thing we want to do is find the discontinuities. And to do this, we just need to solve the denominator. Of course, it's a different situation if you have a square root kind of function, or if you have a piecewise function. But in the case of a fraction, the only time there's discontinuities is if the denominator is equal to 0. And so we can figure out when that happens by doing solve denom of f of x equals to 0. So here we're solving when the denominator of x equals 0. And we see that we get two solutions, 3 and -2. So we can say we have discontinuities at x equals 3 and x equals -2. And that's essentially our part A here. So our part A. Any questions on this part A? All right. Yeah, it should be similar to the one that we did before. Next we have, for each discontinuity, indicate whether it's removable or non-removable. And so to do this, we just need to figure out if these solutions here can be canceled. So if we can remove them, if we can cancel them out, then we're going to consider those removable discontinuities. And the only way we can cancel them out is if they're zeros in the numerator as well as the denominator. And so we know there are zeros of the denominator. We just need to confirm our zeros of the numerator so we can see if any of them are repeats in the numerator and the denominator. And so we'll go ahead and solve our numerator for f of x equals 0. And we see we get two zeros. We get -2 and 0. And so 0 is only a 0 for the numerator, and so we don't care about it too much. But this one here, that is both in the numerator and the denominator, is going to be one of those zeros that can be removed. We can cancel it out because it exists in both the numerator and the denominator. And so we're going to say that x equals -2 is a removable discontinuity. And because we couldn't remove it, by the fact that we couldn't remove it, we can say that x equals 3 is a non-removable discontinuity. So essentially, by not being cancelable in this step, we know that the other one is non-removable. So anybody have any questions in terms of what I did here? So we're just indicating if these are removable or non-removable discontinuities for part B.
May I share the screen?
Sure.
Okay.
Let me.
Mhm.
You can go ahead now.
Okay. So I don't know like what happened here.
Did you try running your f of x again? Or go back to the f of x,
Uh-huh. Yeah,
run
here.
that again.
Okay. Hmm?
It says that there's something wrong with that.
Yeah. Is there anything wrong?
It doesn't look like it. I'd say
Yeah.
just erase it and rewrite it.
Okay.
It's pulling something from somewhere. It's saying that there's a
Okay.
symbol in there that it doesn't like,
Okay.
and then it carried that symbol into the next equation, which it didn't like.
Okay. I will try it
Uh,
later. Yeah. Thank you.
absolutely. Uh, okay. Can you guys still see my share? Just wanna
Yeah.
know. Um, okay. I'm good now. Yep. All right, so now we need to do part C, where it says verify your results graphically, then confirm your results algebraically using the appropriate limit. So they're asking us to graph and find the limit algebraic. All right. And so to graph, we just want to plot our f of x. And to get even more fancy with it, we can always write discount equals show removable. And I noticed looking at my picture, I don't really see the things that I'm interested in seeing. I mean, I do see what happens when x is 3, but I don't know what happens when x is -2. So it looks like by default, the picture is just not what I'm looking for. And so I'm going to add some x values. I'm going to say that x is equal to -5 to 5. And so many times people ask me this question of, hey, how do I know what x values to plug in here? You got to base it on what's the question is asking, right? So in this case, the question is asking to solve for these discontinuities, and it wants us to confirm our result graphically. And so, in other words, we should be able to see our limits on the picture, right? And in this picture, I can see that, hey, when x is 3, I get a vertical asymptote. In other words, there's no value here. And then when x is -2, I get an open circle. And I wanted to see both of these things. I wanted to see what was going on at -2, and I wanted to see what was going on at 3, because that's where my discontinuities existed. And this here confirms what I just mentioned up here, that x is at -2 is a removable discontinuity. We know because we got an open circle. And that at 3, it's a non-removable discontinuity. We know because we got a vertical asymptote. Any questions on the plot? All right. Well, last thing on this piece with part C was finding that limit algebraically. And so the way we'll do that is by using that limit command that we started using earlier. And so we tell it the limit of f of x as x approaches the value that we want to plug in. And in this case, we have two discontinuities, right? We have one at 3 and the other one at -2. And so we can do -2 first. And we see that we get a nice little limit of 2/5. And we're all done here. We confirmed our limit is here. And now we'll notice something a little funny when we do the limit of 3, right? Because we know it doesn't work. And so we do actually get something that tells us, hey, this doesn't work. You get an undefined answer. And so sometimes we can go a little further here and like double confirm that this is extra true by doing limits from the left and from the right. That's why I mentioned those earlier. We can say that here that our limit from the left does not equal the limit from the right. And we can see that by finding them both, right? So if we find them both, we see that our limit from the left is -infinity and the limit from the right is +infinity, which aren't technically numbers. And therefore, we're undefined because we do not have the same limit from the left and from the right. And even if we did, they're infinities. So they're not even considered technically numbers. And so, yeah, so that's about it for this part C. Any questions on this piece? There's one last concept I want to go over, and that is the piecewise function. Piecewise function. That's pretty much one of these down here, where we have given a condition, we plug in a certain function, and then given a separate condition, we use a different function, and then lastly, given a third condition, we use a separate function. So this one here just pretty much tells us that depending on where our x value is, we're going to use a separate function. And Maple has a nice way of plugging these in. So I think I have a sample one down here. I'm not going to use a sample one because this one only has 2. And everybody always asks me, well, how do I make 3? Which is technically what we have here, right? We have three conditions and 3 equations. So I'm going to make one that also has 3 conditions and 3 equations. And so the way we do this is, first of all, we write f of x is, and then we can write the word piecewise. Piecewise. And we want to give it a condition first, then an equation, then a condition, then an equation. So essentially kind of the way this is written, but backwards. Write the equation, the condition first, then the equation, then the condition, then the equation, etc. So let's say mine was x is less than -3, right? and my equation is x squared plus x. So this is my first condition, comma, my first equation. Next, I can hit my second condition. Let's say my second condition is that between -3 less than or equal to x is less than or equal to 3. This is my second condition. You may be asking yourself, how did I get the less than or equal to symbol? Put a less than and then an equal. You do it at the same time, it'll make that symbol for you. You can also come here to the common symbol section and pick the symbol if you would like to do that instead. But a reminder that we can just put a less than symbol and then an equal sign, and it'll make that less than or equal to symbol. Coming back, I have my condition, equation, condition, and so I need my equation. Let's say my equation was just 17x. And now I need one final condition. My final condition can be when x is greater than 3. And I'll give one last function. Let's say it's x cubed plus x. So now I have a condition, equation, condition, equation, condition, equation. If I press enter, we should see it looks just like here on the right, except that mine doesn't have these little commas in between, which is perfectly fine. Just make sure that this right here aligns to whatever is on your picture on the right, and you should be all good. Extra note, there is another way of doing piecewise functions. You can write f of x is, and then come up here and click this thing. It'll make this, and you can fill it out. So if I was to do the same problem, I could write x squared plus x here. Change this to x is less than -3. This is 17x. And then this is less than or equal to . And to add a row, you right-click it and hit Insert Row. And you see that it'll add these question mark rows, and we can go ahead and fill these out. So I can write 3 x and x cubed plus x. And we see that this works just like this. Doesn't matter if it's pinkish purple, doesn't matter if it's this color or if it's the regular black color, it will work either way. So please feel free to use either the piecewise command when doing that problem or use this thing. Personally, I like using the piecewise command because I'm, from the old school, we had to do it this way. And I think that this is one of those things that are a little clunky compared to some of the other shortcuts in Maple. So not my favorite shortcut, but it works. So if you want to use it, please feel free to do so. I think this one appears a little more consistent. So I like this one a little more. But yes, that's not what I'm here for. I'm just here to let you know the options, and you guys can tackle it as it works best. So yeah, this is actually it that I have for new content today. I'm gonna stop the recording here and let you guys start working on your labs. I'm gonna post this content up on the board so that you have it. You can feel free to copy anything from it. Remember, it's all code, so don't feel like you're doing something wrong by copying. It's what we're supposed to be doing. It's code. We just should be copying things and changing the pieces that we need to change where necessary. And